To predict voltage loss at a ground fault interrupter or GFI outlet under a specific amperage load, you can use a digital multimeter with a clamp meter function. Here's how: firstly, set the multimeter to the clamp meter function. Secondly, connect the clamp around the conductor feeding the GFI. Thirdly, apply the appropriate amperage load to the circuit, for example 8 amps. And fourthly, read the voltage on the multimeter. This measurement will indicate the voltage drop at the GFI under the given load. A significant voltage drop at the GFI under reasonable loads could indicate underrated wiring or daisy chaining instead of pigtails with GFI in series. To calculate the voltage drop from the load and wire size, use the following formula: voltage drop equals load amperage times wire length times resistance divided by 1000, where load amperage is the amperage of the load being applied to the circuit. Wire length is the total length of the wire from the transformer to the GFI round trip. Resistance is the resistance of the wire per foot, available from wire tables. If the calculated voltage drop is greater than the observed voltage drop, it could indicate underrated wire or improper wiring, such as daisy chaining. As a precaution, only qualified electricians should perform any work on the 120 volts electrical system. Verify the voltage drop at the GFI using the provided tool to ensure proper system operation and prevent potential overloads or safety hazards. Let's delve deeper into understanding voltage drop and its implications for electrical circuits. Voltage drop refers to the decrease in voltage along a conductor due to the impedance of the wire. Impedance includes both resistance and reactance, but in typical low voltage wiring scenarios, resistance is the dominant factor. Several factors influence voltage drop. These factors are the length of the wire, the cross-sectional area of the wire, the amount of current flowing through the wire, the material of the wire, and the temperature of the wire. Longer wires will have a greater voltage drop than shorter wires, assuming all other factors remain constant. This is because there is more material for the current to travel through, leading to increased resistance. Thicker wires, meaning wires with a larger cross-sectional area, will have a lower voltage drop than thinner wires. This is because the larger cross-sectional area provides less resistance to the flow of current. Higher currents will cause a greater voltage drop than lower currents. This is due to Ohm's law, which states that voltage is equal to current times resistance, or volts equals amps times ohms. Copper is a better conductor than aluminum, meaning it has lower resistance. Therefore, a copper wire will have a lower voltage drop than an aluminum wire of the same size and length carrying the same current. The resistance of a wire increases with temperature. Therefore, a wire at a higher temperature will have a greater voltage drop than a wire at a lower temperature. Voltage drop is important for several reasons. Excessive voltage drop can cause equipment to malfunction. For example, motors may not start properly, lights may dim, and electronic devices may not operate correctly. Voltage drop causes power loss in the form of heat. This power loss is wasted energy and can also lead to overheating of the wires, creating a fire hazard. National Electrical Code, or NEC, sets limits on the allowable voltage drop in electrical circuits. These limits are typically 3% for branch circuits and 5% for feeders. Branch circuits are the circuits that supply power to individual loads such as lights and outlets. Feeders are the circuits that supply power to branch circuits. There are several ways to reduce voltage drop in electrical circuits. You can use shorter wires, use thicker wires, reduce the current, use copper wires instead of aluminum wires, keep the wires cool. To calculate voltage drop, you can use Ohm's law and the wire's resistance per foot. The formula for voltage drop is voltage drop equals current times resistance. The resistance can be found in wire tables, which are available in the NEC and other electrical reference materials. Here is an example calculation. Suppose you have a 120 volt circuit with a 100 foot length of 12 American wire gauge, or copper wire carrying a 15 amps load. The resistance of 12 AWG copper wire is approximately 1.588 ohms per 1000 feet. Since the wire is 100 feet long, the resistance is 0.1588 ohms. Using the voltage drop formula, voltage drop equals 15 amps times 0.1588 ohms equals 2.382 volts. The percentage voltage drop is voltage drop divided by source voltage times 100. In this case, 2.382 volts divided by 120 volts times 100 equals 1.985%. This is below the NEC 3% limit for branch circuits. Now let's discuss the implications of using a digital multimeter with a clamp meter to measure voltage drop at a GFI outlet. A digital multimeter is an essential tool for any electrician. It can measure volts, amps, and ohms, as well as test for continuity. A clamp meter is an accessory that can be used with a multimeter to measure current without having to break the circuit. This is particularly useful for measuring current in AC circuits. When using a multimeter with a clamp meter to measure voltage drop at a GFI outlet, it is important to follow these steps. Firstly, turn off the power to the circuit at the breaker box. Secondly, plug the multimeter into the GFI outlet. Thirdly, attach the clamp meter around one of the wires feeding the GFI outlet. Fourthly, turn the power back onto the circuit. Fifthly, read the voltage and current measurements on the multimeter. The voltage measurement will indicate the voltage at the GFI outlet. The current measurement will indicate the amount of current flowing through the circuit. The voltage drop can be calculated by subtracting the voltage at the GFI outlet from the voltage at the breaker box. If the voltage drop is excessive, it could indicate a problem with the wiring, such as undersized wires, loose connections, or corrosion. It is important to correct any problems with the wiring to ensure safe and reliable operation of the electrical system. In the context of low voltage lighting systems, voltage drop can be a significant concern. Low voltage lighting systems typically operate at 12 volts, which means that even a small voltage drop can have a noticeable impact on the brightness of the lights. This is why it is important to carefully calculate the voltage drop in low voltage lighting circuits and to use appropriately sized wires. When designing a low voltage lighting system, it is also important to consider the length of the wire runs. Longer wire runs will result in greater voltage drop. To minimize voltage drop, it may be necessary to use multiple transformers or to locate the transformers closer to the lights. It is also important to use high-quality connectors and to make sure that all connections are tight and secure. Loose connections can cause increased resistance and voltage drop. In addition to voltage drop, it is also important to consider the ampacity of the wires used in low-voltage lighting systems. Ampacity is the maximum amount of current that a wire can safely carry. The ampacity of a wire depends on its size, material, and insulation type. It is important to choose wires that have sufficient ampacity to carry the load of the lighting system. If the wires are too small, they can overheat and create a fire hazard. The NEC provides tables that list the ampacity of different types of wires. These tables should be consulted when designing a low-voltage lighting system. When working with electrical systems, it is always important to follow safe work practices. Here are some safety tips. Firstly, always turn off the power to the circuit before working on it. Secondly, use insulated tools. Thirdly, wear safety glasses. Fourthly, never work on electrical systems when you are wet or standing in water. Fifthly, if you are not comfortable working on electrical systems, hire a qualified electrician. And sixthly, follow all applicable electrical codes and regulations. Now, let's address the side question regarding daisy chaining versus pigtailing GFI outlets. Daisy chaining GFI outlets involves connecting multiple outlets in series, where the load from one outlet passes through the next. This method is generally not recommended for several reasons. Firstly, if one outlet in this series fails, all downstream outlets will also lose power. Secondly, daisy chaining can increase the voltage drop to the downstream outlets. Thirdly, it can make it more difficult to troubleshoot problems. Pigtailing GFI outlet involves connecting each outlet directly to the circuit's neutral and hot wires using short lengths of wire called pigtails. This method is generally preferred because it provides a more reliable and safer connection. Firstly, if one outlet fails, the other outlets will continue to function. Secondly, pigtailing minimizes voltage drop to each outlet. Thirdly, it makes it easier to troubleshoot problems. When installing GFI outlets, it is important to follow the manufacturer's instructions and to use the correct wiring methods. It is also important to test the GFI outlets after installation to ensure that they are working properly. GFI outlets are designed to protect people from electric shock. They work by detecting imbalances in the current flowing through the hot and neutral wires. If an imbalance is detected, the GFI outlet will trip, cutting off the power to the circuit. GFI outlets should be installed in areas where there is a risk of electric shock, such as bathrooms, kitchens, and outdoor locations. It is important to test GFI outlets regularly to ensure that they are functioning properly. To test a GFI outlet, press the test button on the outlet. The outlet should trip, cutting off the power to the circuit. If the outlet does not trip, it should be replaced. Let's delve a bit more into calculating voltage drop using the formula provided. The formula is voltage drop equals load amperage times wire length times resistance, divided by 1000. It's important to ensure consistent units. Load amperage is measured in amps. Wire length should be in feet. Since resistance is typically given in ohms per 1000 feet, the division by 1000 adjusts for this. Resistance is the resistance of the wire per 1000 feet obtained from wire tables. For example, let's say you have a circuit with a load of 10 amps, a wire length of 200 feet, and you're using 14 AWG copper wire, which has a resistance of approximately 2.525 ohms per 1000 feet. Using the formula, voltage drop equals 10 amps times 200 feet times 2.525 ohms per 1000 feet divided by 1000 equals 5.5 volts. This means that there is a 5.5 volts drop along the wire. To determine the percentage voltage drop, you would divide the voltage drop by the source voltage and multiply by 100. If the source voltage is 120 volts, then the percentage voltage drop is 5.5 volts divided by 120 volts times 100 equals 4.21%. This is above the recommended 3% voltage drop for branch circuits, indicating that a larger wire size may be needed to reduce voltage drop. When performing voltage drop calculations, it is important to consider the entire length of the wire run, including both the outgoing and return paths. This is why the wire length in the formula refers to the total length of the wire from the source to the load and back. In addition to wire size and length, the type of wire insulation can also affect the ampacity of the wire. Different insulation types have different temperature ratings, which affect the amount of current the wire can safely carry. The NEC provides tables that list the ampacity of different wire types based on their insulation and temperature rating. When selecting wires for an electrical circuit, it is important to choose wires that are rated for the appropriate voltage and temperature conditions. It is also important to ensure that the wires are properly protected from physical damage. Wires that are exposed to physical damage should be installed in conduit or other protective enclosures. Conduit is a rigid or flexible tube that is used to protect electrical wires from damage. There are different types of conduit available, including metal conduit, PVC conduit, and flexible metal conduit. The type of conduit that is used depends on the specific application. For example, metal conduit is typically used in commercial and industrial applications, while PVC conduit is often used in residential applications. Flexible metal conduit is used in applications where the wires need to be bent or moved. In addition to conduit, other types of protective enclosures can be used to protect electrical wires. These include junction boxes, pull boxes, and enclosures. Junction boxes are used to connect multiple wires together. Pull boxes are used to provide access to wires that are being pulled through conduit. Enclosures are used to protect electrical equipment from the environment. When installing electrical wiring, it is important to follow all applicable electrical codes and regulations. The NEC is the most widely used electrical code in the United States. The NEC is updated every 3 years, so it is important to use the latest version of the code. Electrical codes and regulations are designed to protect people and property from electrical hazards. By following these codes and regulations, you can help ensure that your electrical system is safe and reliable.